I have not always been in my current science teacher form. I was once younger, thinner, cooler, and better looking. Then I began to grow, mentally, spiritually, and of course, physically, to the point that I weighed 210 pounds of nerdy awesomeness. But I had ambition to weigh less, to become more attractive to the ladies. So where did I go? If you said the gym, you're so wrong. I went straight to the moon where I lost 175 pounds instantly, making me a drop-dead gorgeous 35 pounds of ladies' man. But Mr. C, you say, you look exactly the same. Well, my friend, you are right, because mass does not equal weight. Mass is the amount of matter an object has. Unfortunately, I have the same number of atoms on Earth as I do on the moon. Whereas weight depends on gravity. So on the larger Earth, I weigh more because the Earth is so much bigger than the moon. Bigger Earth equals more weight, versus smaller moon equals less weight. So what did we learn? Mass is not weight. Mass is the object's amount of matter. Weight is how we measure gravity. And while going to the moon will help me lose weight, it won't burn off those troublesome love handles.
Hi class, Mr. Wirtz here again, going over our last video on metric mania on mass. First of all, comparing the English to metric system, which is larger, 1 pound or 100 grams? Number 2, 1 kilogram or 1 pound? And number 3, 1 ounce or 1,000 milligrams? 1 pound is bigger than 100 grams because 1 pound is equal to 453.6 grams. So that 453.6 is obviously bigger than 100 grams, which is what the pound is equal to. 1 kilogram or 1 pound? The kilogram is bigger. Basically, if you take away the 0, for every 10 kilograms, it's 22 pounds. So if you look at a kilogram is actually bigger than a pound. And finally, 1 ounce is bigger than 1,000 milligrams. If we take the conversion that 1 ounce is actually 28,349.5 milligrams, that number, 28,000, is a lot bigger than 1,000 milligrams. I'd really like to have that gold though. I bet you would too. Mass refers to the amount of matter in an object. The base unit of mass in the metric system is the kilogram and is represented by the letters kg. The standard where it came from, 1 kilogram is equal to the mass of the International Prototype Kilogram, a platinum iridium cylinder kept by the BIPM at Sèvres, France. It's a very important lab in France. We don't really need to remember that, but that's just kind of the history behind the kilogram. When looking at metric units and conversions, we have 1 kilogram is equal to 1,000 grams. Remember the prefix that we learned, kilo, equals 1,000. 1 gram equals 1,000 milligrams. Milli was one of the prefixes we learned as well. So knowing that, which is larger, 1 kilogram or 1,500 grams? Well, if we know 1 kilogram is equal to 1,500 grams, if we put it over here, 1,500 grams would be bigger than 1,000 grams. Letter B, which is larger, 1,200 milligrams or 1 gram? Well, we know that 1 gram is equal to 1,000 milligrams, so 1,200 is bigger than 1,000. Letter C, 12 milligrams or 12 kilograms. Well, basically 12 milligrams, or excuse me, 1 gram is equal to 1,000 milligrams. So 12 milligrams would be even much smaller than a gram. So we know that 12 kilograms is much larger. And finally, if you have 4 kilograms or 4,500 grams, well, for every 1,000 grams, we can work backwards here, is equal to 1 kilogram. So 4,000 grams, if you take the 4,000 and leave the 500, that would be equal to 4 kilograms if you use this conversion. But since there's 500 more, 4,500 grams is more than 4,000 grams. When we measure mass, we'll be using actually not a triple beam balance, but something very similar called a double beam balance to find the mass of various objects. And you're going to watch a video in just a moment to see how to do that. The objects are placed on the scale. For example, you could put some dice, some stones, whatever you want to weigh, or not weigh, I'm sorry, measure the mass of. And then you basically move the weights and the beams on the side until you get everything to line up. So this is a little bit different than what we're using, but this next video will show you exactly how our double beam balance is going to work when we practice.
Today, we are going to explore how to use a double beam equal arm balance. And we're just going to call it a double beam balance. Notice that I did not call this a balance scale. I did that because it's not a balance scale. A scale determines your weight, and your weight is a measurement of how gravity affects your mass. On this balance, we are just going to measure the mass of two objects. That's why we're not calling it a balance scale. First thing we have to do when we go to use a double beam balance is we want to make sure that it is zeroed. By that, we want to make sure that this little pointer is lined up on the black line. Okay? To do that, we have to make sure that the two beams, this lower beam and this upper beam, are both on 0. This bottom beam moves in increments of 10, and you can hear it click as you move to different increments, okay? We want to make sure that 0 is in the center of the window, since we're trying to zero the balance. This top beam, we want to make sure that it is also pointing on 0. And this is where the patience factor comes in. Once this pointer stops moving, hopefully it's lined up with the little black line behind it. See this little white piece with the black line? We want that line and the pointer to line up with each other. If by some chance they don't line up with each other, ask your teacher to turn this little silver knob over here, because you have to turn it just a little bit and wait for this pointer to stop moving. And most kids turn it too fast and too quickly and don't give the pointer a chance to catch up. So if it doesn't line up when you move the two beams to the left and put them on 0, ask your teacher to turn this little knob right here that I'm pointing to. It looks like it's zeroed, so we're going to measure two household objects today. We're going to measure the mass of a cell phone, and we're going to measure the mass of, you guys know what this is, PSP. Let's start with the PSP. You guys are probably more excited about that. PSP. So we're going to put the PSP on the left platform. Notice how the platform's changed, okay? Now we need to move these beams to determine the mass of the PSP. So I'm going to just move it to, say, 100. Notice we have no change. That means that this PSP has a mass of more than 100 grams. Let's move it to 150. This platform still hasn't moved up yet, so we need to keep moving it until we see this platform rise a little bit. Move it all the way to 200 grams, and now, see how the platform's starting to rise? See how our needle, our pointer is starting to move? We're getting close to the actual mass of this PSP. You're probably saying, "What? We can't move this bottom one any further to the right." That's why we have the upper beam. We move the upper beam over, and I'm just going to move it to 1 gram and see what happens. Now, you see how the pointer's moved past the center line? We want this pointer to line up with the center line each time we measure the mass of something, because that will tell us the actual measurement. Since this pointer's past this line, I have to move this top beam a little bit to the left. So I'm going to move it a couple tenths, because this top beam measures from 0 to 10 grams. And each gram measurement is broken down into tenths. So each of these grams is broken into 10 parts. And right now I'm waiting. It looks like we need to move it a little bit more to the left. So we'll move it another 1/10 of a gram. And this is where patience comes in. We have to wait for this to stop moving. Once the pointer stops moving, it lines up on that black line. And it looks like it's lined up. So let's figure out how many grams this PSP is. It's 200, and this pointer is not on 1 gram, so we have to count the tenths. These little lines, each line is 1/10 of a gram. So we have 1, 2, 3, 4, 5. It looks like 6 grams, but not 6 grams, 6/10 of a gram. So this PSP has a mass of 206/10 grams, or 200.6. Okay. Now we'll go ahead and take the PSP off. Let's go ahead and put everything back to 0. You should always do that before you start measuring a new object. And we're going to measure the mass of the cell phone. So put the cell phone on the left platform, and let's slide this to 50, nothing. Slide this to 100, nothing. Slide it to 150. Oh, see movement? Once this platform starts rising, that lets us know we're getting close. Let's move it to 180. Whoops, way too much. 170, way too much, because the platform is all the way up. We want these to be balanced. That's why they call this a balance scale. Or not a balance scale, but they call it a balance. To 160, that doesn't work. 150. Okay, 150 is not enough. 160 is too much. So we need to move it to 150 and do what? That's right. We need to move the top beam. So let's move the top beam to about 2 grams. And look, the platforms are not balanced. This left one is higher than the right, so we need to get them balanced. So let's move this back a little bit. Let's move it to 1 gram. 2 grams was too much. Remember, we're watching the pointer up here. We want it to line up on the black line. When it lines up on the black line, that means we're good. And we can go ahead and count how many grams we have, and we'll have an accurate measurement. Looks like it's just a little bit to the right, so I need to move this ever so slightly to the left. And there we have to wait and see if it lines up on the black line. I think this might be it. Still moving just a little bit. Alright, so now the pointer's lined up on our little black line. Now we can count how many grams we have. And we have right down here 150 on the bottom beam, and on the top beam, this little pointer is on 1 gram exactly. So the mass of the cell phone is 151 grams. 150 plus what we have on the top, 150 plus 1, 151 grams. And that is how you use a double beam equal arm balance, or double beam balance.